Morning, afternoon, or evening. We're going to get into our 6th day. So we're basically our max min stuff that we did the first 5 days of this unit is basically finished now. So now we get into the second part of the unit, which is a related rate. So what is a related rate, as I will explain in a minute. And then we're going to look at spheres. So just explaining it verbally before I write anything down. A related rate would be a rate it's something that's changing with respect to time in a shape or volume or area or something like that. So, for example, if you're blowing up a balloon, the volume of the balloon is increasing so many cubic centimeters per second. Related to that would be the growth of its surface area and maybe the growth of its diameter. Those would also be growing at some rate, and they're related, so they're called related rates. And that's what we mean by related rates. So if we were to define that a little bit in terms of what it is, we could say that a related rate, let's get my, there we go. A related rate in calculus is a dimension or measurement, we'll say, that is changing with respect to time when I use with respect to, I usually use WRT sometimes for shorthand, but if you see that in my corrections and stuff, that's what that means. So a related rate in calculus is a measurement that is changing with respect to time in a shape that's not really the way I want to put it. It's changing with respect to time, affecting, that's what I want, affecting all other measurement changes within the problem, we'll say. And then we'll just kind of do a little example. If a sphere is growing in volume at a given rate, that the radius of growth will be related to the volume growth. Okay, so that's basically what a related rate is. Not my best English, I'm sure. Let me just get my timer out here so I can keep track today. We're only going to do sphere. I'm going to do the sphere examples today only. So we'll do 2 examples, and then there's 4 practice problems that you'll do. Kind of do it all in one shot. So today's video should be in that 30-minute range or less. Okay, so when we write related rates, we relate them as derivatives, because derivatives are changing rates. Okay, so if I get to my marker here. Okay, so we can write them. We can write them as relate. So if we had something like dA dt, and the A represented area, this would be change in area over time. per unit of time. Okay, so volume might be dV dt. Okay, surface area might be SA dt, dSA dt, or whatever, however you want to write it. Radius might be dr over dt, and that kind of idea. And there'll be some unit to it. So area would be centimeters squared per minute or second, and volume would be like centimeters cubed per second. So they're rates. Okay. So when we're working with spheres, which is what we're going to get into now, I'm going to do two sphere problems. We have to know the sphere formulas. Okay. So we need the formulas for spheres. So when working with spheres, the following formulas are used. Okay, so we know, first of all, the volume formula. So volume equals 4/3 pi is not a variable, it's a number, r cubed. R is a variable. So volume is related to radius. That's volume. This is radius. Okay, and then we have surface area of sphere, which will go SA. Okay, that is equal to 4 pi r squared. Okay, r is the same, and this is surface area. Okay, and we have one for circumference. Circumference around a sphere is just pi equals 2 pi r. If we're writing it in radius form, if we're writing it in diameter form, it would be pi d, but I can keep everything in radius form for now. So this is circumference. Okay, and we also know that the area of a circle, if we need it, is pi r squared. Okay, this is circumference, and we know that 2r equals d, which is, this is the diameter. Okay, so there's our relationships that we'll need to use. So we're going to get right into using these, and I'll show you how to do them. And I'm going to start off with a multi-step question using related rates with spheres. And then we'll do another one. Probably only going to do the two because that's probably all we'll need. Fairly simple to do this. You're always going to be taking derivative with respect to one of the variables to time, either volume, radius, circumference, or something like that. Okay, so I'm going to flip ahead here, and my first example here is example. You are inflating a balloon so that the radius is increasing at a rate of 2 centimeters per second when the balloon has a radius of 4 centimeters. So it always tells you when it's happening. Find how fast the circumference of the balloon is growing, B, how fast the surface area is growing, and C, how fast the volume is growing. So we're going to do all three of those. So the first one we're going to do is circumference. So the first thing is you have to define what you know first. So step one is define the rates in the given question. So step one, define your rate, your given rate. Okay, so we have the radius is increasing. So let's call it dr dt. Radius is changing per unit of time, and that is equal to 2 centimeters a second. Okay, at r equals 4. Okay, because maybe it's not inflating at the constant rate. Okay, so that's our given rate, step 1. Step 2, and we'll go with A now. Step 2, take the formula and do differentials. We'll call it derivative. Sometimes they call it differentials because you're doing it with respect to time when time isn't in there. So let's take the formula for circumference. So we know that the circumference of a circle is equal to 2 pi r. So what we do is we do differentials. So we say dc dt is related to, and now we do this one. 2 pi is a number. We take the derivative of r. The derivative of r is 1. And then we go dr dt for the rate. Okay, so what you're doing is you're doing, let's call it differential so we don't get confused between derivative and differential. And do okay, so you're doing a derivative of these two because you're relating those two rates together, circumference to radius. Okay, now that you have it, you can plug in your results. Step 2 that was. Step 3 is plug in the results. Now it was to calculate. Okay, so if I were to do that, dc dt would equal 2 pi times dr dt, which is 2 centimeters a second. So therefore, our answer is dc dt is 4 pi centimeters a second. Now, if you didn't want it in terms of pi, you could take that pi and multiply it out by 3.14 if you'd like. So 4 times 3.14 is the 12 point, whatever, 56 or something. So you can go 4 pi on your calculator like that and figure out what it is. 12.56 or 57 centimeters per second. And that's all you have to do for that differential. Now, there are more difficult derivatives to do in here. Now, spheres are the easiest because they only have an r involved in their formulas. When you have more than one variable, it gets a little more difficult. But right now, with spheres, it tends to be the easiest one. That's why we start with it. So circumference is growing by 4 pi centimeters a second. Now, if you left it like this, 4 pi centimeters a second, I would correct that. Say that's correct because pi is a number, right? This here, you could change it into decimal if you like. So let's do the surface area one next. Okay, so B. Let's do our 3 steps. Okay, we've identified what the rate is up here already, so we're going to leave that. But let's do our second step. Write the formula for surface area. Okay, the surface area of a sphere is equal to 4 pi r squared. So now we're going to have to do differentials with surface area and r here. Okay, so let me move this down a little bit so we can see a little bit better and make a little more space. There we go. Okay, so we're going to go dSA over dt. So the rate at which the surface area is changing will equal, this is a number, 4 pi. Okay, now we have to do the derivative of r squared. So the derivative of r squared is 2r times dr dt. So if you're any variable in there, you have to times it by the related rate that you know at the top. So there's our formula. So if we simplify our formula, that's going to be 2 times 4 pi, which is 8 pi, r times dr dt. Now you can see why we needed to know what the r value was, because there's an r still in that formula. So take a look up here. It was 4 centimeters. So we're going to now plug in step 3, 2 centimeters for dr dt and 4 for r. And we'll get our rate for surface area. So this is going to be 8 pi times 4 centimeters. Keep your unit in there because the units change, and times 2 centimeters a second. Okay, so now if we multiply that together, we get 8 times 4 times 2. So that's 64 pi centimeters squared per second. Now that makes sense now that you're getting surface area, because it should have centimeters squared per second. Now that's a good answer. If you wanted it in a decimal form, you could go 64 times pi. 64 times pi here. Oops, wrong pi button. Okay, so where is it there? There it is. Okay, so 64 pi, and if we convert it, it's 201.06, or 201, if we round it off, centimeters squared per second. Okay. All right, so let's do the last one in that first example. See? What about how fast the volume is growing for a sphere? Let's do C over here. Okay, the volume formula for sphere is 4/3 pi r cubed. Okay, there's only one variable in there that changes, so it's related to volume. So we're going to get dv dt. Okay, now 4/3 pi is a number. Pi is not a variable, it's a number. So we just leave it out there. And then we take the derivative of the r cubed, so that'd be 3r squared. And we go times dr dt. Now you have to be careful. Sometimes they'll throw diameter, and then you have to convert the diameter into radius and stuff like that, so be careful. Okay, so now we can simplify this. Okay, so 4/3 times 3 is 4. So it's 4 pi r squared times dr dt. Okay, because the 3's will cancel out there. And now we just plug our results. 4 pi. Now the r at that rate was 4 centimeters squared times 2 centimeters a second. Okay, so we've got 4 pi times 16 square centimeters times 2 centimeters a second. Okay, so 4 times 16 times 2, that's 4 times 32, like 128 or so. So we've got 128 pi centimeters cubed per second. That's the volume, so that makes sense, right? Okay, and if you wanted that in times pi here, So if you wanted it in number form, it's 402 centimeters cubed per second. And that is the very beginnings of related rates. Okay, so we're about 20 minutes in. We'll go another example here using related rates, and then I'm going to give you 4 practice questions to do today with related rates and spheres. I'll show you them. And then tomorrow we'll get into related rates with cones, which have 2 variables in them, so we have to do some converting of variables and things like that. And then we'll do some mixed ones, I think, as well. Maybe some cans and things like that, like cylinders. Okay, so last example that I want to do with you today is this one here on the next page. Okay, a beach ball is being inflated at 20 centimeters per second of growth to its circumference. So notice that circumference, right? When it has a diameter. Now that's a diameter, not a radius. So there's some tricks in here. 30 centimeters. How is the volume of the beach ball changing? Okay, so this is one where we're not given dr dt. So what we have to do is we have to solve for that dr dt from the circumference equation, because circumference is not in the equation for volume. Okay, so it's a bit of a different way to do it. Okay, so we know, let's start with step 1. Step 1 is to identify what we do know first. We've got dc dt at equaling 20 centimeters per second. Okay, now with the circumference is equal to 2 pi r, and the volume, which is we want to find dv dt. Okay, and we know that volume, not dv, sorry, volume is equal to 4/3 pi r cubed. So we don't have a c in the next formula. So we have to figure out what dr dt is by using this formula. So find dr dt using the circumference formula. First. Okay, so we know that if we take that formula and we go dc dt, that is equal to 2 pi, and the derivative of r is 1, dr dt. Okay, now we have to solve it for dr dt. So let's plug in our value. 20 centimeters a second equals 2 pi dr dt. So divide both sides by 2 pi. So dr dt is 10 over pi centimeters a second, which we'll round it to a decimal area. So let's go 20 divided by 2 pi. And we get 3.18. And I'm not going to round it off to 1. I'll just round to 2 so that it's a little more accurate. 3.18. I'll go even 3 because why not? 3. And the units don't change because there's no unit here to cancel out on the bottom, so it's still centimeters per second. Okay? Don't forget, I forgot to identify in here that the diameter is 30 centimeters. Therefore, the radius equals 15 centimeters. We do know that too, when this particular rate is being used. So we did that, and then we did step 2 here. So once we've done that, then step 3 is to go to the volume formula. Okay, so then finally, use the volume formula. Okay, so that's our third step. Okay, so our volume, I'm going to write it out first, the 4/3 pi r cubed. We now know that dr dt is this, so we can plug it into here once we do the differential. dv dt is what we're trying to find. That's going to equal 4/3 pi times, take the 3 out front, r squared dr dt. Same as what we did before. So if we do that differential, we get dv dt is equal to 4 pi r squared dr dt. Okay, now we plug our values. We know what r is. That's the 15 centimeters. And we know what dr dt is. So we can now plug our values. Sorry guys. I'm going to write 11 there for whatever reason. 4 pi times 15 squared, centimeters squared, times 3.183 centimeters per second. Okay, so let's get our calculator out. 15 squared, 225, times 4, times pi, times 3.183 equals. Okay, so I get 8,000. Let's see here. 8,999.72. So it's about 9,000. So dV, and there could be some variance depending on how you round off here. If you rounded that to 3.2, it might be a little higher. So let's say it's about 9,000 centimeters cubed per second. And this is our final answer here for question. So sometimes you have to break it down. And that is related rates with circles, the easiest kind. So I've got 4 examples here. I'll bring over my sheets here. I haven't done the solutions yet, but I'll make sure I do those as well. Okay, so if we come over here, we are on day 6 and sphere-related rate problems. If we click here, don't do these bonus ones here unless I didn't put any solutions for those, but just do the top 4 ones here. Okay, these 4 here. Don't worry about these 4 down here. I don't even know why I put them in there. Probably just because I scanned the page and didn't edit it. Just do the top 4. Don't do the bonus ones. Okay, and next day, we'll get into our next type of related rate question. Okay, and I'll put the solutions up underneath as you saw there. So good luck with that, and we'll get into the more complex related rates a little bit tomorrow.